All right, so now we want to start practicing. So we want to verify that that big F is the antiderivative of little f. So what we decided in the intro video is that I can decide if something is an antiderivative by taking a derivative. Okay, so what I'm asking is this thing the antiderivative of this thing? So the way I can find that is by taking the derivative of this and seeing if I get this. Okay, so what is the derivative of capital F of x? And that derivative is drop your exponent out front, drop your exponent by 1, drop your exponent out front, drop your exponent by 1, and then minus 1. And then, so yes, the answer is it is an antiderivative. But remember also that this went to 0, and that constant could be anything. So remember, that's going to be where we come up with the constant of integration. Okay, so now we want to try it again. So I have g of x, capital G of x, and I'm going to compare it to little g of x. Capital G of x is 8x squared. Okay, little g of x is 16x. So I want to know, is capital G of x the antiderivative of little g of x? So how do I test? I take a derivative of capital G of x, and I end up with 16x, and I get the exact same thing. So yes, it is. All right, so big G of x is the antiderivative of little g of x, because when I took the derivative of big G of x, I got little g of x. All right, so now we're going to go a step further. We want to find all of the antiderivatives of g of x. So that's where that plus c is going to come into play. Okay, so I know that this is the antiderivative of this. But what I'm going to do is tack a plus c on there, because remember, I can have any constant at the end of there, and when I take a derivative, it goes away. So I have to have some way to represent that there could have been a constant there. That constant could be 0. Okay, but I still need to represent that. So now this is an antiderivative. Now this represents all antiderivatives. Okay, that represents all the antiderivatives because I can have any constant on the end of there. And so I have the general solution. We call it the general solution, or the or all antiderivatives. Okay, so now what I want to do is graph the thing. Okay, so when I graph it, what is this going to look like? So when I look at the original function, my original function is 8x squared. What does 8x squared look like? 8x squared looks like a parabola that got stretched by a factor of 8. And then what would the plus c do? The plus c would just move it up or down on that axis. So anytime you add a constant to the end of a function, it's just going to give a vertical translation. So it's either like if we had the plus 7, okay, that would take this parabola and move it up 7 units. If I had minus 3, it would take this parabola and drop it down 3 units. So you could have any number, an infinite number actually, of all of these parabolas that would satisfy the general solution, okay? Because it's still 8x squared, but where did it get shifted up or down to? That's the question, okay? So now we are going to practice some more. So we have, that was number 1, that was number 2. So now we have number 3. We've got g of x, capital G of x, is 2/3 x cubed. And I want to compare it to little g of x, which is going to be 2x squared. Okay, I want to know, is this the antiderivative of this? Okay, so going from here to here, it's a derivative. Going from here to here, it's an antiderivative. Okay, so I can say yes, because when I take the derivative of capital G of x, I end up with drop your exponent out front, and the 3's reduce, drop your exponent by 1. So I get that general, or I get that specific solution. Well, now what's the general solution? So all of the antiderivatives are going to include a potential constant that when I took its derivative, it went away. Okay, so now I would like to know, well, what does that graph look like? So this graph is going to be of a cubic function that got a little bit morphed, okay? And all the plus c does is take it and move it up and down from the original graph. And these are all supposed to have little tails on them, okay? So it's just going to take that original 2x cubed and shift it up and down on the axis. All right, so now let's introduce the actual notation of integrals. So I have find the indefinite integral. So remember that indefinite means I'm just finding the formula. I'm not going to find the width of the area under the curve. Okay, so I'm just finding a general formula. So I have the integral of 5 dx. Okay, so remember, anytime I want to find the integral, I'm going to increase my exponent by 1. So remember that there is an x to the 0 out front. I'm sorry, there's an x to the 0 sitting there. Then I'm too lazy to write. I'm going to increase my exponent by 1, so that gives me an x to the first, divided by my new exponent. And don't forget that 5 is coming along for the ride. And when I clean that up, I get 5x plus c. Okay, so I increased my exponent by 1 and then divided by my new exponent. So what does that mean? I need to show you a different way to write this because this is a constant multiple. And remember, with derivatives, sometimes we would just move that constant multiple out of the way. I can do that with this as well. So that would say 5 times the integral of dx. Well, remember that there's a 1 sitting there. So I can rewrite 1 as x to the 0. Increase your exponent by 1, divide by your new exponent, and then plus c. The other thing is, remember that this integral symbol, as soon as you do what it says to do, it goes away. So I have integrated, so that symbol goes away. Where did the dx come from? We introduced that notation when you took a derivative. So when you take the antiderivative, it goes away. Okay? So let's try it again. I have the integral of the square root of 3 dx. So your question is, where is my variable? My variable is what I'm integrating. So I can move that constant out front and just realize that there's an x to the 0 sitting there. So increase your exponent by 1, divide by your new exponent, and don't forget about your constant multiple. So now I have the square root of 3 times x. That x is not under the radical. And then plus capital C for the constant of integration. What if I have the integral of x to the 5th dx? Okay, increase your exponent by 1, divide by your new exponent, plus c, and you're done. Okay, let's try it again. We have 4 times x to the 9th dx, and you could rewrite that as 4 times the integral of x to the 9th dx. Okay, when I integrate that, when I write it this way, I'm just stating that the 4 is coming along for the ride. Okay, it really doesn't matter, but knowing that you can do that later on is going to be extremely important. Okay, so I'm going to increase my exponent by 1. So that gives me 4 times x to the 10th over 10 plus c. But 4 over 10 can reduce to 2 over 5. X to the 10th plus c. Okay, so let's try it again. We have the integral of x to the negative 5 dx. So remember, I'm going to increase my exponent by 1. So be careful. That means you're getting closer to 0. If you think about it on a number line, when you increase, you move from left to right. When you decrease, you move from right to left. So if I'm at -5, I need to increase to -4. So I'm going to increase to -4 and divide by my new exponent, and then use my plus c, and that's it. You're done. Okay? So the integral of 2 times t to the -8 dt, and notice now this notation for the derivative tells me what my variable should be. So if we come back over here, all this said was 5 dx. Well, that tells you what your variable should be. If it said dm, then I would have been using m's. If it said dy, I would have been using y's. Okay, so I have this dt. So now just notice that this derivative notation matches the variable that you're using. So I'm going to increase my exponent by 1 over -7, and then plus capital C. Okay, and we're done. All right, so I have x to the 6/7. So I'm going to increase my exponent by 1. So 6/7 plus 7/7 is 13/7 divided by 13/7. Okay, and now it gets a little bit messy. So when we start dealing with rational exponents or exponents that look like a fraction, okay, remember that when you divide, you're actually multiplying by the reciprocal. Okay, so I could say that this is times 7/13, x to the 13/7 plus c. So that's something I'm going to get in the habit of doing, is when I increase my exponent by 1, I'm actually multiplying by the reciprocal. So just like this, I increased to -4, and I multiplied by -1/4. Okay, it's just that it showed up in the denominator. So again, I'm probably going to end up skipping to this step. So just know if I'm dividing by a fraction, I'm going to multiply by its reciprocal. And I'll say that the whole time. But if you're just like listening to this on mute, then that might be an issue. All right, so I have the integral of 8u to the 7/8 du. So I'm going to increase my exponent by 1. So 7/8 plus 8/8 is 15/8. Divided by my new exponent means I flip and multiply. So instead of divided by 15/8, it's times 8/15, which gives me 64/15 u to the 15/8 plus capital C. Plus capital C. All right, so let's try one more, and then we'll shift to a second video. So I have the integral of 1/3 x to the 4th dx. So be very, very careful. Your constant multiple is 1/3. Okay, so I'm going to change my exponent to be a negative exponent. So my constant multiple of 1/3, I just brought it out front so it's out of the way. And I brought my variable up top with a negative exponent. Okay, so all I've done is rewrite. I have not done any calculus. But don't bring that 3 up top. Okay, only bring the x up top by changing the sign on the exponent. So now I'm going to increase my exponent by 1. So I get x to the -3 over -3, which means what I really have is -1/9 x to the -3 plus c. Okay, and there's a variety of ways that you could write this. I could leave that as 1 over, I could leave it like this, or I could say -x to the -3 over 9. So I could just multiply across the top, multiply across the bottom. Or I could rewrite it using positive exponents, which would be -1 over 9x to the positive 3rd. And being a lazy math person, I just stick with the first one that I write unless I absolutely have to change. Okay, so we're going to finish up the last couple because they have to do with ease. So we'll finish up the last few on the next video.